So, I'm Crystal. I'll talk to you guys today about the selection of Lyman alpha emitting galaxies using Bayesian photometric redshift. So I'll start by introducing what Lyman alpha emitting galaxies are and why they're important. And then I'll talk about the goals of this investigation and how we selected these galaxies in the data. After, I'll show you the results, and then I'll conclude my presentation. So what are LAEs, or Lyman alpha emitters? These are galaxies that emit Lyman alpha radiation from hydrogen. So in this figure to the right, you'll see that this is an energy level diagram for the hydrogen atom. So if there's an electron in the n=2 state that falls down into the n=1 state, it'll emit a photon at about 121.5 nanometers. And this is what we call Lyman alpha radiation. And so these galaxies are galaxies that emit this type of radiation, and they typically contain a very large fraction of the young stars. And they're likely to be progenitors of Milky Way type galaxies. So they're excellent ways of studying galaxy formation and galaxy clusters. So now we know that they're really important. So how do we actually see them in our data? So in this investigation, I wanted to identify LAEs in the ODIN, or the 100 square degree dark energy camera imaging in narrowband survey. And so to do this, we needed to have some steps laid out. These steps were first to force the Bayesian photometric redshift software, or I'll call it BPZ from now on, to assume that all galaxies in the ODIN survey data that we have to have a redshift of z=3.1. And then we'll interpret those with an acceptable goodness of fit as the LAE candidates that we're looking for. And then we want to compare this to the selection of LAEs that we get made with color cuts. So we want to compare methods. So diving into how we did our investigation, first we need to get the ODIN catalog that has 2.2 million galaxies, approximately, worth of photometry in each band. And this includes the N501 and N673 narrowband filters, which are specifically designed to detect emission lines of the type that we're looking for that will detect Lyman alpha emitters. So what we do is we give the BPZ software our catalog from ODIN. And in this catalog, like I said, it's going to give BPZ the photometry, meaning flux densities and the error in flux densities. And BPZ is going to calculate the photometry for an entire library of template galaxy spectra. And what it does is it compares the photometry of the templates to the observed photometry, and it's going to try to match one of the templates to the photometry that we see for each galaxy. And this way we can find a best fit match template and also a redshift. So to start, what we did is we had these two catalogs besides our own ODIN catalog. We also have the HSC catalog, which is very useful because it already has redshift recorded in the catalog. So we found galaxies that were common to both of these catalogs. And then we gave these galaxies, we fed them into BPZ. And so on the y-axis, this is the redshift that we get out of BPZ. And we compare it to the redshift that's recorded in the HSC catalog. And what we see is that BPZ is pretty much doing what we want it to do. For the most part, in this trend here, you can tell that BPZ is mostly assigning pretty much the same redshift that is recorded in the HSC catalog. So we know for the most part, it's doing what we want it to do. So how exactly do we use it to identify LAEs? Well, we're going to use it in a completely different way. We used BPZ in a way where we restricted the redshift of the entire catalog to z=3.1. So we basically told BPZ, okay, pretend that every galaxy in this catalog has a redshift 3.1. And then we calculate, we use a chi-squared analysis to determine whether or not it's which galaxies actually have this true redshift. So we can choose the galaxies that might actually have a redshift of z equals 3.1 by selecting the ones that have a chi-squared value less than 7. So in our results, in this plot on the right over here, you can see that when we gave the entire catalog to BPZ, this is the chi-squared distribution of all galaxies in that catalog. However, if we compare it to the restricted catalog where we told BPZ to pretend that every single galaxy has the same redshift 3.1, we get a very different chi-squared distribution. And this is really good, actually, because what it's doing is saying that BPZ actually found that most galaxies in the restricted catalog are not actually, they don't actually have a redshift of 3.1. In fact, the galaxies that are, we can confidently say have a redshift of 3.1 lie over here in this part of the chi-squared distribution, where the chi-squared value is actually very low. So what do we conclude from this? We know that in the restricted catalog, only about 1.4% of galaxies have a chi-squared value less than 7 when we restrict to a redshift of 3.1. And so moving forward, we know that we're going to compare the galaxies to the Lyman alpha emitters that we identified through color cuts to see how well our methods compare to the methods that have been used in the past. And we'll also be able to restrict BPZ to fit at a different redshift 4.5 so that we can also look at the LAEs that are detected by the N673 narrowband filter, not just the N501 narrowband. And this is very, very important because LAEs are used to study the large-scale structure of the universe at high redshift. So we want to be able to identify as many as possible so that we get a good representation of galaxies in our data. But at the same time, we want to be careful about which ones we actually select to make sure that we're not choosing galaxies that aren't actually Lyman alpha emitters, because they'll end up contaminating our sample. So I want to give a huge thank you to my advisors and mentors, Eric Weiser and Adam Broussard, and for allowing me to collaborate with their lab group. And obviously, I want to give a huge thank you to the SNSP scholars and the administrators, to Casey, Hakeem, Stefan, to Abigail, and obviously have to say thank you to the Flatiron Institute and the Simons Foundation for having all of us. Thank you so much.
Okay, are there any questions for Crystal? So Everett?
Yeah, I have two questions actually. So for the photometric redshifts, according to the HSC model, yeah, that one. So are the outliers significant at all?
So some of them, like these sorts of like straight lines or bands that you see are kind of patterns that show up because of the filters. So some of them are from that, and like you said, others are just outliers. There's also errors in these redshifts as well. BPZ gives us errors in the calculated redshift, but just couldn't spot them here.
Massive. Okay, cool. Yeah. So my second question is with regard to the chi-squared plot. Yeah, that one. So with the restricted Z equals 3.1, I was wondering why is there a dip between what looks like 6 and 8?
That's a great question. I think we'll have to do some more digging into that. I'd have to probably analyze the catalog further because I don't know why there's just a random dip right there.
Thank you.
Also, anybody on Zoom can ask questions. You can just unmute yourself and ask if you have it.
Just one quick question. Why the interest in Redshift 3.1?
Oh, great question. So we're interested in the Redshift of 3.1 because it's the one that's relevant to the narrowband N501 filter. But there are 5 total filters, and there's actually one other narrowband filter. The other narrowband filter is N673, and the redshift that's relevant to the N673 filter is 4.5. So further, we'll be restricting to 4.5 as well. And both of those filters are important to use in our study because the way that we identify Lyman alpha emitters is through an excess in those narrow bands as compared to the broadband filters.